I am Dr. Seema Vats, and today we are going to discuss about work, energy and power. Well, in this lecture we will learn about these concepts that will going to define work done by a force and give the unit of work. We will also calculate the work done by an applied force like gravity when it moves from one point to another, work done by variable forces like spring. We will also define the power of a system and state work energy theorem. Let's discuss about these examples and see what is the work done in these cases. First case, when a man pushes a wall, there is no displacement of the wall. The question arises whether a work is done. Well, we say that the work done is 0 in this case because there is no displacement of the wall. Let's take up the second example in which a man carrying a big load in his hand and he is moving around. Whether a work is done, we again say that the work done is 0 in this case, and similar is the case for a particle moving in a circle. So, the work done is 0 in all the above examples, and to know why is it so, we will talk about what is actually a work done and what is its definition. Well, when we talk about what is work done, we will start with a mass and let's apply a constant force on it. We see that this force displaces the object, and after a certain displacement d, it reaches another point. So, we say when a constant force acting on an object results in a displacement d, that is, it moves by a distance d along a straight line on a horizontal surface as shown in the figure, then the work is done. So, in a way, we can say the work done by a force, that is a constant force, is the product of the magnitude of the force component in the direction of the displacement and the displacement of this object. Mathematically, we can represent this thing as W is equal to F dot D is equal to F cos theta D. The unit of work is joule and the dimension that we calculate for the work done is ml square T minus 2. Now, we will come to the definition of the work, that is what is F cos theta in the expression F dot D. The component of force along D is F cos theta, and theta is the angle between force vector and the displacement vector. We should also know that W is a scalar quantity. It does not have any direction, but it has a magnitude. Since it is a dot product of force vector and the displacement vector, it can be negative, positive or 0. Let's see the case when the work done is 0. When D is equal to 0, that is the displacement is equal to 0, then the work done is 0. That is, no work is done by force whatever its magnitude if there is no displacement of the object. Secondly, if the angle theta between the force and the displacement is 90 degree, then also the work done is 0. The perfect example for this is a coolie carrying baggage on his head and he does a 0 work. Let's talk about the positive work done. There are two conditions on it. First, when the angle between the force vector F and the displacement vector D lies between 0 and 90 degree, then the work done is said to be positive. As can be seen in the figure, the force and the displacement, they both are in the same direction. So, work done is positive in both the cases. What happens for a negative work done? Well, when the angle between the force vector and the displacement vector is greater than 90 degree, then the work done is said to be negative. Secondly, the force applied and the displacement, they are in opposite direction. The perfect example is the work done by a force of friction, which is always negative. When we are considering the work done that is positive, negative and 0, let's see what is the work done by the gravity. Let's take up a mass and we lift it through a height h and it reaches another point, that is P, at a height h above the ground. So, what is the work done in this case? The thing to be observed is that object is lifted against the force of gravity. Therefore, it is Fd cos 180 degree. The question arises, why is it 180 degree? Because F and D are in opposite direction. The force of gravity, that is mg, it is lying in the downward direction, and object being lifted up, it is in the upward direction. Therefore, we have taken the angle theta to be 180 degree and it is equal to minus mgh. What do we get? We have a negative work done by the gravity. But there is a point to be noted here, that is, negative work is done by the gravity while the positive work is done by the person, because a person is lifting the object in the same direction in which he is applying the force. Let's see the case in which the object is lowered towards the earth. The force and the displacement, they both are in the downward direction. Then W is equal to Ft cos 0 degree. The question arises, why we have taken the theta to be 0 degree? Because F and D are both in the same direction. It is equal to positive mgh. This means that the positive work is done by the gravity and the negative work done by the person who is lowering the mass. Now, we have talked about the work done by a constant force, but certainly in our real life, we have a work done by a variable forces. What do you mean by variable force? Well, a force which varies with time is called as variable force. As shown in the figure, we can see a varying force F moves the object from initial position xi to final position xf, and the variation of force with distance is shown by a solid curve, which is arbitrary, and the work done is numerically equal to the shaded area. What is the work done during a small displacement? It is given by W is equal to f of x into x, and this f of x is numerically equal to the small area shown shaded in the figure. So, how are we going to calculate the total work done? Well, the total work done by the force between xi and xf is the sum of all such areas, that is the area of all strips added together, which is given by W summation of fx into x. A perfect example of work done by a variable force is a spring. Then we got to understand what is a spring mass system. A spring mass system is the one whose one end is rigidly fixed and a mass m is attached to the spring. This system rests on a smooth horizontal surface. As we can see in a figure, portion A, in which the relaxed position of the spring is free end at x equal to 0. In the second case B, the spring is compressed by applying an external force F. In the case C, we have the string being pulled or elongated by an external force F, and the maximum compression or the elongation is Xm. There is one interesting thing in a spring, that is Hooke's law. What is Hooke's law? According to Hooke's law, which is true for small x value, f of s is equal to kx, where k is known as spring constant, and since the direction of force Fs is always opposite to compression or extension, it is written as F is equal to Fs is equal to minus kx. Let's examine the work done by this spring. When the spring is compressed, external force and the displacement is towards the left, as can be seen in the figure B. So, the work done by the external force is positive. Secondly, the restoring force generated by spring for the same displacement is towards the right. Therefore, the work done by the spring is negative. In this case, we have to show mathematically the work done in the case of spring and the value of spring constant. In the first case of figure A, we have at s equal to 0, the force Fs is equal to 0, that is, there is no restoring force acting in a relaxed position. But as x increases, that is, the displacement increases, the force Fs increases and it becomes equal to F when x is equal to maximum. Maximum is the maximum strength at which the string can be stretched. Third case, we have Fs average force during compression or extension. It can be taken as Fs by 2. The question arises, why can we take Fs is equal to Fs by 2? Since force Fs is varying linearly with the displacement d, therefore we can average it out to be Fs by 2. Therefore, W is equal to F dot d. Now here force is Fs, Fs by 2 dot x is the displacement, and since Fs is equal to kx maximum, by putting the values we will get the expression for the work done by the spring is equal to half k x maximum square. We can also measure the value of spring constant by using this system, that is a spring mass system, in which the mass is attached to a string. In this case, the weight of the mass which is acting downwards due to gravity is given by mg, and the string is stretched to the maximum, that is x. Therefore, we have Fs is equal to the gravitational force, which means that mg is equal to kx and k is equal to mg by x. In this way, we can measure the spring constant of a spring. Then we can also know about the unit of this spring constant. It is given by Newton per meter. Since now we are aware of work done by a constant force and a variable force, and we have discussed the examples, let's come to the power. That what is power? Actually, the rate at which work is done is called as power. Mathematically, we can express average power is equal to work done divided by time taken. W is the work done in the time t. It is defining the average power. Now, the SI unit of power is watt, which is equal to joule per second. And the dimension when calculated comes out to be ml square t minus 3. Power is a scalar quantity. It has only magnitude, no direction. There are different expressions for power in different units, that is 1 kilowatt is equal to 10 to the power 3 watt, 1 megawatt is equal to 10 to the power 6 watt, and 1 horsepower is equal to 746 watt. Now, let's discuss about the concept of power. What actually power is doing? Power shows us the time that work requires. That is, if there are two different people doing the same amount of work in different time, they have different amount of power. Suppose a 40 horsepower engine could accelerate the car from 0 mile per hour to 60 mile per hour in 16 seconds. If this were the case, then a car with 4 times the horsepower could do the same amount of work in 1/4 of the time. That is, a 160 horsepower engine could accelerate the same car from 0 mile per hour to 60 mile per hour in 4 seconds. Now, let's know about the unit kilowatt hour. What actually it is? The unit of power is used to define a new unit of work, that is energy. One such unit of work is kilowatt hour. This unit is commonly used in electrical measurement. 1 kilowatt hour can be written as 1 kilowatt into 1 hour. 1 kilowatt is equal to 10 to the power 3 watt and 1 hour is equal to 3600 seconds. When we take the product of these two, we get 10 to the power 3 joules divided by 1 second into 3600 second. So, 1 kilowatt hour comes out to be 3.6 into 10 to the power 6 joules, which is equal to 3.6 megajoules. The electrical energy that is consumed in our homes is measured in kilowatt hour. In common man's language, 1 kilowatt hour is equal to 1 unit of electrical energy consumption. Let's talk about energy. That what exactly is energy? We know that the capacity to do work is called as energy. A system having energy has the capability to do the work, like an automobile moving on the road uses chemical energy of the fuel. Similarly, we can have different types of energy which can be used for various purposes. But in universe, there are two types of energy, mainly kinetic energy, which is the energy by virtue of motion, and secondly, potential energy, which is by the virtue of position. Basis on this, the kinetic energy, there is a very important theorem, work energy theorem. This theorem, it relates the work with the energy. How? This theorem states that the work done by the resultant of all the forces acting on a body is equal to the change in the kinetic energy of the body. That is, if the initial kinetic energy is given as K1 and the final kinetic energy is equal to K2, then the work done on this body is equal to K2 minus K1. Let's discuss about the kinetic energy. What kind of energy is it? We know that kinetic energy is by the virtue of motion. Secondly, it is a scalar quantity. What is the expression for kinetic energy? It is depending on the product of mass and the square of the speed. That is, half mv square determines the kinetic energy. The question arises, can we have a negative value of kinetic energy? Well, possibly not. because there are two conditions. First, mass can never be negative, and secondly, velocity which can be negative, we have a square term that makes it positive. Therefore, we have kinetic energy to be equal to positive. Similarly, we can discuss about potential energy. What is a potential energy? Object possesses this energy due to their position in the space. And what is the perfect example for this? It is the energy possessed by a body in a gravitational field and called as gravitational potential energy. Let's calculate the potential energy in a gravitational field. And how are we going to do it? Let's take a Earth's surface. In this, we have a mass at a height h1. We take the mass against the force of gravity to a point that is at height h2. So, a mass has been displaced from position h1 to h2 against gravity by a distance h, which is given by h2 minus h1. There is another interesting point, that is magnitude of F, that is a force due to gravity, is mg and it is acting downwards. Therefore, the work done by the person who is lifting the mass is equal to F dot d is equal to mgh. The important concept here is the change in the height, that is h is equal to h2 minus h1. The work done is positive and it is stored in the mass in the form of gravitational potential energy. Therefore, a point on the surface of the earth is assumed to be the reference point with zero potential energy. Now we have potential energy of springs. Whenever we talk about the potential energy of springs, we have the work done by external sources to compress the spring is given by half kx square. This work done is stored in the spring as elastic potential energy. When the spring is left free, it bounces back. And the elastic potential energy of the spring is converted into the kinetic energy of mass m. Now, since we have discussed about work, power and energy, let's talk about the law of conservation of energy. The law of conservation of energy states that the total energy of an isolated system always remains constant. That is, energy is neither created nor destroyed. Energy may change its form, it can be converted from one form to another, but the total energy of the system remains unchanged. Let's talk about the example of energy conversion. Well, in a thermal power station, the chemical energy of coal is changed into electrical energy. This electrical energy runs machines, and in these machines, the electrical energy changes into mechanical energy, light energy or thermal energy. Now, we will summarize whatever we have done in this chapter. That is, we have learnt about the work done by a constant force and a variable force, in which we have tackled with the different examples in which the work is done by the gravity and as well as by the spring. We talked about the power, we talked about the energy and the potential and the kinetic energy. We have also noticed the law of conservation of energy and the work energy theorem, which are all interrelated topics and that give you insight into these concepts more and more if you go through it in detail. Thank you.